part of the question is, what is the longest rotation period of the wheel that will prevent the riders from falling off at the top? So we're trying to find out the longest rotation period that will keep them from falling at the top.
Mm-hmm.
So we know we have one rotation period, but I don't necessarily know how they expect us to find the second rotation period. Or how to find the longest rotation period.
I'm going to erase all of that stuff.
What factors come into play?
So at the very top, you have to have some centripetal acceleration, right? In order to make it all the way around the top of that circle. So in order to get that centripetal acceleration, what are the forces that cause it?
At the top we have the normal and gravity.
So the slower and slower you go, what happens to your normal force?
It decreases.
At the top, yeah. So eventually, the slower you go, the smaller normal force gets, until when?
Oh, that makes so much sense. Until gravity overweighs the normal force, and then you drop.
Well, not necessarily until gravity outweighs the normal force. Because remember on the last problem, or on the first part of that problem, the gravity, or the normal force was, at the top, was 318.
Okay, so when gravity has a bigger magnitude?
No, because mg was, what's 55 times 9.8?
3.
Be like
539.
So at the top before, you had 539 newtons of gravity that were pushing her towards the center, and 318 newtons of normal force pushing you to the center. So it's not when normal force drops below gravity. What happens if you were to get to the top? So what does the normal force become if at the top you fall?
0.
Yeah, because you're no longer in contact with it. But right up until that point, right when it hits 0, you're still in contact, right? It's possible to be in contact with something but have the force between the two things be 0.
At that split second.
Mm-hmm. So as you slow down, your normal force will get smaller and smaller and smaller and smaller until it hits 0. And if it's 0 at the very top, you're okay, because you're not going to fall, because it'll come back around and catch you again. But what happens if you try to go slower than that?
Then you fall.
Mm-hmm.
So we want to find when the normal force is less than 0?
Not when the normal force is less than 0, because that would be, well, that can't happen, right? But right at the moment the normal force is 0, and you still only have centripetal acceleration. Because what happens is, after it hits 0 and you start slowing down more, this would be your sum of forces. Let's see here. So your forces in the radial direction, you have, you sum them up, so you've got force of gravity plus the normal force. And those equal ma sub r plus ma just in general, moving in that direction. So as long as these two add up to be this, then this doesn't have to come, right? So as long as these two can add up to be, like, as long as this is enough to cover both of these forces, then you're not going to fall. This would be like acceleration just falling. That make sense?
Okay, so the ma counts for acceleration of the fall.
Yeah. So as long as you have enough radial acceleration to account for both of these forces, then you're fine.
Okay.
But as you bring radial acceleration down, normal force can shrink, right? You can get smaller and smaller and smaller. But once normal force hits 0, can this side of the equation get any smaller?
No.
So what happens if you start slowing down this side of the equation? So you get to the point where it's just Fg equals ma sub r. Can this side get any smaller?
No.
It's just the force of gravity. But what if you try to make this a little bit smaller?
Then gravity would get larger.
Well, gravity will be too large to stay in circular motion. You're going to have to add a little piece that's going to make you fall. Does that make sense?
Yeah.
So that's what's called a critical speed. I think the book talks about it if you want to look at it more. So why does the water stay in the bucket? Let's see. Okay, so this is critical speed right here. So the slowest speed at which the car can complete the circle. Because here, you've got the normal force pushing you down and gravity, right? You make normal smaller and smaller and smaller until finally it's 0, and at that point you'll still stay on the track. But if you go any slower, you're going to get up to the top and you're going to fall before you ever make it to the top. Okay?
Mm-hmm.
So the critical speed is when you make normal force 0.
Okay, that makes sense.
So then how do you find your slowest possible, or the longest possible period from this?
Well, if our normal force is going to be equal to 0, we want to find the rotation right at 0, and we know that if it's right at 0, then we're going to have the largest period.
Mm-hmm. So that would be this case right here, where we don't have any normal force, but we also still don't have a force that's kind of like accelerating us down to actually fall. So like that.
Okay. We know AR is omega squared of R. We have M is equal to mg. Now the m's can cross out, and the g is equal to omega R times R, or g can also be equal to v, the velocity squared divided by R. But I would
Okay.
think we would want to solve for omega.
Mm-hmm.
So omega, first we get gravity divided by omega squared is equal to R.
Do we want to divide omega squared or R though?
R,
Because we're solving for omega.
right. So omega is equal to the square root of G over R. So I
And
have.
actually, that's, let's just say that. Yeah, so this is the minimum velocity, but there's another equation for minimum, like the critical angular velocity, and that's what it is R over the square root of R over G. So, you're right. It's kind of cool the way that it works. That always is the case. The critical speed the critical angular velocity will always be that. So if you want to find the slowest possible speed, you can go around the loop. All you need to know is the radius.
So we'll take the square root, gravity was negative 9.8 divided by 8. No, it can't be a negative 9.8, it has to be positive 9.8.
Right, so G is actually a positive value. It usually ends up being negative because we look at it in like the plane that we're looking at.
I get 1.1.
1.10, what's the units on this? What'll be the units for this?
Seconds squared. Seconds.
Well, it's an omega, right?
So it would be revolutions per 1 second, or
Not revolutions. So revolutions would show
radians
up,
per second.
but radians, yeah. Radians is kind of that disappearing unit. Sometimes it goes away. We don't know why. We know why, but okay. So now I've got an omega.
And I'm solving for speed.
The longest possible period of rotation.
So now I don't know what to do.
So you remember what we did last time? Let's see. So remember we started with the period last time and we just said 1 revolution over 4.5 seconds?
Mm-hmm.
And we used that as our omega?
Mm-hmm. And convert it to radians per second, and then multiply that by the radius.
Right. So what if we change this back into revolutions and then made it, or we found out how many? So like, this was, an omega is an angle over time.
Mm-hmm.
So if you want you want to find the time, you can change this, right? Omega over, or the angle over omega equals time. Does that make sense?
Mm-hmm.
So what's the angle for 1 revolution?
1.1 radians.
Well, so just the angle. How far do you want to go in this amount of time? Full revolution, so 2 pi radians. And then you put your omega down here.
Oh, wow.
And these cancel, and your S comes to the top. You end up with units of seconds, which is what you want.
Wow. I would never have thought about that. That is so cool. So basically we're like, okay, so we need to find our omega. And find our omega by our force diagram in our summing up all the forces. And then we're like, okay, omega is theta over time, but if we want time, we have theta over omega. And we take theta, which is 2 pi radians, and divide it by the radians in which we found, divided by the seconds. And so the radians cross out and the seconds move to the top. Okay, cool.
Or we could have switched this to revolutions per second, and then done the same thing with 1 revolution over that.
Mm-hmm.
Really. So that would be, whatever that time is, 2 pi divided by 1.1 is 5.67, is that what it is?
Mm-hmm.
So that's the slowest, that's the longest time that you can take to go around that loop without people falling off.
That's not very long at all.
Mm-hmm.